Electrical hazards and risk reduction by design. Proper design of an electrical system can reduce the risk associated with the use of electricity to an acceptable level. To achieve a safe electrical system, the design effort needs to identify and account for all existing hazards, and aim to either reduce the possible consequences or reduce the probability of occurrence of hot surfaces, incendiary sparks, electrification of persons by direct or indirect contact, etc. Examples include reduction of voltage levels, avoiding contact by screens, guards, and shields, conductor sizing to limit temperature during normal operation, detection and elimination of fault conditions, limiting exposure to the hazardous condition. 1. Extra low voltage (ELV) systems. The International Electrotechnical Commission (IEC) has adopted standard voltage values that are considered sufficiently safe. Extra low voltage (ELV) is defined as not exceeding the relevant voltage limit of 50 V AC RMS and 120 V DC. In a dry skin condition, this extra low voltage can be assumed safe to touch for an indefinite period of time. In wet skin conditions, lower voltage levels need to be observed since the contact resistance is significantly lowered, 25 V AC and 60 V DC. 2. Grounding, protective earth, and earth connection systems. The protective earth concept aims at reducing the risk resulting from indirect contact. The basic intent is to avoid elevating the electrical potential of the casing of an electrical apparatus to a dangerous voltage level with reference to the Earth's surface. Main factors to be considered are the earth connection system used, type of protective system used, power supply type and voltage level, cable design calculation results, environmental conditions with respect to exposed persons. 3. Short circuit and overload protection. Short circuit and overload protection of electrical circuits plays an important role in risk reduction as it relates to thermal hazards. Additionally, short circuit protection limits the consequences of high mechanical forces occurring due to magnetic effects in short circuit conditions. For a technical component, cable, bus bar, switchgear, or other device, to survive a heat surge and the related mechanical stress, the time required to switch off the current needs to be very short. Common operating times range from a few milliseconds up. 4. Insulation. The primary function of electrical insulation is to separate current-carrying conductive elements from other parts, components, and elements. Levels of insulation include insulation, all the materials and parts used to insulate conductive elements of a device. Functional insulation, insulation between conductive parts, necessary for the proper functioning of the equipment. Basic insulation, insulation of hazardous live parts. Supplementary insulation, independent insulation applied in addition to basic insulation. Double insulation, insulation comprising both basic insulation and supplementary insulation. Reinforced insulation, insulation of hazardous live parts providing a degree of protection against electric shock equivalent to double insulation. Whether or not any of the various types of can considered for safety purposes depends upon the circumstances and environment. 5. Arc flash protection. An arc flash protection strategy will encompass a number of techniques such as arc flash containment / arc resistant equipment, current limiting fuses, arc flash detection and high-speed switching, arc flash quenching, remote operation, strict application of safe work procedures. Personal protective. Labeling and marking. 6. Overvoltage protection. The design of overvoltage protective systems is based on both the coordination of the maximal voltage surge that equipment can withstand, and methods to limit the voltage surges passed on to the equipment. Strategies include preventing atmospheric overvoltages from entering the electrical system, prevention of overvoltage originating from switching actions, automatic supply disconnection, surge suppression.